first problem we're going to focus on in dynamic programming is the shortest path problem. We've seen the shortest path problem in a lot of context, and here's just an additional context. In this context, we're given as input a directed acyclic graph. We're also given a start node and a terminal node, S and T, and we're given a distance between I and J for every arc, ij. The objective is to find the shortest path from S to T. We should be familiar with this problem by now. We already know how to solve this problem. We can formulate an integer program for this problem and take the linear programming relaxation and solve that. Since this has a totally modular constraint matrix, this is going to give us an optimal solution. We can also model the shortest path problem as a flow problem. We can also solve the shortest path problem with a primal dual algorithm, which is a more combinatorial algorithm. So there's no surprise that we can solve this problem efficiently with another solution technique, dynamic programming. But now we're going to solve it with dynamic programming. Remember the three ingredients that we need to set up a dynamic program. First, we need to identify a set of subproblems. Then we need to identify a function that can compose these subproblems into solutions to larger problems. And finally, we need to find the smallest subproblems and find the value of the solution for them. In this case, our subproblem is going to be the distance from S to I, which we're going to call capital D of I. We're going to need a small piece of notation to define our function. This piece of notation is going to be delta minus I. This is the set of all arcs that are directed into I. Here we have a small example graph, and we're going to make a few observations on it. We're going to focus on node 6. Delta minus of 6 consists of the nodes 1, 2, and 5. And now we can notice something about a shortest path from S to 6. There's really only three alternatives. Either we can take a path from S to 1, and then from 1 to 6, or we can take a path from S to 2, and then 2 to 6, or we can take a path from S to 5, and from 5 to 6. In each of these cases, we take a shortest path from S to that node, and then take the particular arc from that node down to 6. To find the shortest path, we take the smallest of these three alternatives. We either go through node 1, we go through node 2, or we go through node 5. Taking the minimum of these is going to find the shortest path from S to 6. And so that's going to give us the value of D6. We can wrap this up into a nice recursive function. Suppose we're looking for the shortest path from S to I. Then what we do is we take I, we look at all the nodes that come before I in the directed acyclic graph, delta minus of I. And among all these nodes, we look at all the paths that go through exactly this node, and then take the final arc from that node to I. Taking the minimum over all these possible paths is going to give us the shortest path from S to I. Now we have some of the ingredients for our dynamic program. We've identified the subproblems we'd like to use, the shortest paths from S to I. And we've identified a recursive function that allows us to build up solutions to larger problems out of solutions to smaller problems. We still need one more ingredient, which is sort of the base case, but we also need to put these two ingredients into a framework that allows us to actually compute things. For example, when we're computing the shortest path from S to I, we actually need to have computed already the shortest path from S to J for all j in delta minus of I. So this object needs to be computed. So we need to be sure that we compute all of these objects in exactly the right order. This is where the topological sort comes in. We're going to sort the nodes according to the topological sort. If we order things according to O, then whenever we compute the shortest path from S to I, we're going to be guaranteed that we've already computed the shortest path from S to J, because J comes before I in this topological sort. We actually don't need to use the entire topological sort. We only need to compute this value for the nodes between S and T, where S is V of S and T is V of T. Our base case is simple. The distance from S to itself is going to be set equal to 0. This is the smallest subproblem, it's the only one we need a constant value for. Now we're going to compute the distance from S to VI for all I between S and T in our topological sort O. And we're going to compute them in the order of the topological sort. Whenever we get to T, node t, we know that this is the shortest path from S to t, and so this is our optimal solution to the shortest path problem. Now we'd like to prove that this dynamic program is actually correct, that is, it returns the optimal solution. We do this inductively, and in general, for every dynamic program, we're going to have some sort of inductive proof that the dynamic program is correct. The inductive proof starts with the base case. We say that for all the cases where we've set a constant value that it makes sense. In this case, the shortest path from S to S is 0, so the base case makes sense. The meat of these proofs usually rest inside of the inductive case. To do the inductive proof, we have to induct on something, and in this case, we're going to induct on the topological sort. That is, we're going to look at the indices of the topological sort. So we fix one of the indices of the topological sort, and for every lower index, we're going to assume that the claim is true. In this case, assuming that the claim is true, says that the shortest path from S to Vj is contained in D of Vj. Then we note that if we look at delta minus of Vi, that is this index I we're looking at, this is a subset of all of the subproblems that we've already computed. We have D of Vj computed for all of these nodes in delta minus. Now we start working with the intuition. Any shortest path to Vi has to go through some node in delta minus I, and we're going to call this node V. After it goes through V, it has to take the arc V to Vi. The length of this path is going to be the length of the shortest path from S to V plus the length of arc V to Vi. The length of this shortest path is certainly going to be equal to the minimum length of all paths that go through nodes in delta minus I. Because of the inductive hypothesis, that is, that we already have the shortest path computed for all of these nodes, we know that this is actually the shortest path, D of V, and that inside of this minimum we also have computed all of the shortest paths. And so now we can conclude that the actual shortest path is going to be achieved by our recursive formulation. This proves the inductive case. The final thing we'd like to analyze is the running time of this algorithm. In this case, we're going to implicitly assume that we've used some memoization technique, and so the time that it takes to compute this dynamic program is going to be some function of the number of subproblems. The total running time is going to first take into account how long it's going to take to do our topological sort. We won't go into the details of this running time, but we can imagine that a topological sort is going to take at most order v squared time. Then we have to look at how many subproblems there are. There's going to be a subproblem for every vertex, so there's order, the number of vertices, subproblems. The time that we spend in each subproblem is looking over a min of at most v particular values. So taking a min of v values is going to take order v time. These two things together are going to take order v squared time. So our algorithm is going to take order v squared time for the topological sort, and then order v squared time for the actual dynamic programming execution. And so the total runtime of our algorithm is going to be order v squared.